Hey, what's up? Welcome to my channel. My name is Christian and today I'm really excited to share with you how I built a search engine from scratch. In this video, we are not only going to explore the most common techniques and concepts behind search engines, but we're also going to get into the very heart of the technology that powers the web. We'll discover the data structures, search algorithms, and optimization techniques that enable search engines to index and search through billions of web pages in a fraction of a second. And most excitingly, we are going to create our own search engine. If you are passionate about this kind of stuff and you want to learn how search engine works, you can't miss this video. So without further ado, let's get started. The first thing we're gonna do is to identify the different parts our system should have. Let's see step by step what we're gonna build. To the user, a search engine is basically a page with a text box where you can type what you want to search for, and a result page that will show the different pages that match our search. So the first thing we need is a graphical interface with these properties. Now we need to bring this UI to life. We'll connect it to an API that will receive as input the search term provided by the user and return the list of results. Inside this backend, we'll have the searching and sorting logic. These results must be stored somewhere, so we need some kind of database that will contain all the information of the site that we have previously indexed. And finally, we need a mechanism to feed that database. We're gonna build a web crawler in order to surf the World Wide Web and find new pages to store information inside our database. Now let's dive into these parts in order to understand the details and try to figure out how to implement it. As I mentioned before, we'll have a page with an input that collects the user's search term and a results page that will display the information. These results will have the following format: the title of the page where the results were found, the link to the page to be able to click on it and navigate there, and finally a small preview of the content of the page. We'll also need to know how many results have been found with our search term. This will be useful for the pagination system. Okay, now we need to describe how our API and our search engine work. This part is crucial because the structure of the information that we store in our database will depend on these use cases. First, we need to receive the user's input, separate it into different words, and search in our database which pages contains these words, combine the results, and sort them based on several parameters. Let's have a look at this part in a bit more detail. The sorting logic will have a hierarchy with the following parameters. First, the results that contains the greatest match with the search term will be shown. Then, those in which the search term have the smallest distance between them. That is, if your search is pet stores in New York, it is not the same to get a result like this than like this. The closer the keywords are in the resulting pages, the more relevant it will be for the search. Another factor is how important is a word within the page. It is not the same for a search term to appear in the title of the page than in the footer. So we will prioritize that the search terms are located in HTML tags with a higher hierarchy. For this, we can define a hierarchy map that assigns a numerical value to each HTML tag, and we will store the importance of each word based on this. Finally, we will take into account how important or popular are the pages we are returning. This way, we will ensure to prioritize the highest quality content to appear in the first results. But let's stop for a moment. How can we determine how important a web page is? Should we look for a list with the most visited websites and guide ourselves with this information? Surely there is a more efficient and accurate way to do it. What if we take into account the number of web pages that link to a particular page? The more mentions your website has, the more important it will be. So we can rank them based on the number of incoming links to that page. Easy, right? Well, not that much. What happens if you create a million of garbage websites whose only purpose is to point to your online store and hack the search results to always appear first? We must find a way to determine the relevance of a web page without having this kind of problems. But wait, luckily someone has already done it for us. During the 90s, the first internet search engines like Yandex and AltaVista had many problems ranking web pages according to their importance. Some solutions had been tried that didn't quite work, until 1997, when a couple of Stanford PhD students, Sergey Brin and Larry Page, came up with the solution that would open a new era for the internet, the PageRank algorithm. 1 year later, they created Google, which quickly converted into the undisputed king of the internet. But how does the algorithm that gave life to this iconic search engine work? Let's have a look at it. What you're seeing right now is the formula for calculating the ranking of a specific page. But before exploring, let's remove this part to keep it simpler. But don't worry, we'll come back to it in a moment. This formula can be read as follows. The page rank of a page A can be defined as the sum of the page rank of all the pages that point to A, divided by the number of outgoing links from those pages. In other words, to determine the page rank of A, we must obtain the page rank of all pages that point to A, and divided by the number of links that pages have. The fact that the rank of a page depends on the rank of another, and that one depends on the rank of another one, sounds like a circular dependency that won't take us anywhere. But there's a way to solve it. Let's see an example. We have this small collection of 5 pages that point to each other, and we need to calculate the ranking for each one. The first thing we'll do is to initialize all the pages with the same value, which will be 1 divided by the number of pages. In this case, 1 divided by 5, which is 0.2. Now, to calculate the page rank of A, we look at which pages point to A, which are D and E. We have that the rank of D is 0.2 in the previous iteration. We divide this by the number of outgoing links from D, which is 3, and we have that 0.2 divided by 3 is 0.06. Now let's focus on the page E. E has a page rank of 0.2 in the previous iteration, and it contains only one outgoing link, which means that we got 0.2 divided by 1, which is 0.2. Now the new page rank of A is 0.06 plus 0.2, which is 0.26. Now let's calculate the page rank of B. B has 2 ingoing links, A and C. The page rank of A in the previous iteration is equal to 0.2. and it contains only one outgoing link. We say 0.2 divided by 1 is equal to 0.2, and the other ingoing link is C, which also have a value of 0.2 in the previous iteration with a unique outgoing link, which means that the new value of B is 0.2 plus 0.2, which is 0.4. And we continue doing the same with every page. If you notice, the more iterations we do, the result is refined more and more, and it will be nice to continue to the infinite until we have a perfect result, but we don't have that much time. So at some point, when we see the results are stabilizing, we can stop and assign that ranks to the pages. Now that we have the basics, there are 2 problems that we might face. One of them is when a case like the following occurs. As you can see, we have a page that doesn't have any outgoing link, so it can't distribute its rank to others. What will happen if we iterate over and over is that this page will end up with a rank of 1, the highest possible, and the rest of pages will end up with 0. Basically, this page has become a parasite, draining the energy from the others and benefits itself. This problem is known as a dead end, and the easiest way to solve it is, whenever we detect a dead end, instead of it not pointing anywhere, we'll make it to point all the other pages, even itself. This way, we distribute the value evenly and don't affect anything else. The second problem we might encounter is when two or more pages point to each other, but they don't have outgoing links to any other site. This case is kind of similar to the dead end, but it occurs between multiple nodes on the network. When calculating, we'll keep bouncing from one page to another without being able to escape. This is known as a spider trap, and the way we can get out of them is as follows. Sometimes, with a certain probability that we will call D, instead of following the links that the page points to, we'll jump to any other page in the network randomly to continue the calculation. This value is known as damping factor, and it's a number that usually ranges between 0.1 and 0.15. This way we can escape the spider traps and can start calculating safely. And now we are ready to understand the complete formula. By the way, let's keep in mind that this is how the Google's algorithm works in the 90s. Nowadays it is much complicated, with a bunch of crazy things that Google doesn't want you to know because that's their business. But this helps us to have a little approach. It was intense, but now we have an elegant way to rank our pages. This is a very interesting topic, and you can find a lot of articles, papers, books and resources over the internet about it. Personally, I would recommend this book, Google's PageRank and Beyond, from Amy Longville and Carl Mayer. It's an amazing material that goes deep into the origin, functioning and improvement of this magnificent algorithm. But let's not stop here, we must continue our journey. So let's add this part to our layer architecture and continue. We are almost ready, we just need one more detail. Normally, we are not so good while typing, and we often make mistakes when writing our search term. Other times, we are not sure how something is spelled, but even then, we search and we get the results we need. How can we achieve something similar? Let's talk a little bit about fuzzy search, and to implement something like this, let's start from the simple. First, we need to determine how similar two words are. To know this, we'll base ourselves in what is known as the edit distance, which is simply the number of characters we should insert, delete or replace in a word to make it equal to another. For example, if we have the words elephant and relevant and we want to determine their edit distance, let's see how many operations we need to perform to convert one word into the other. In this case, if we take the word relevant and we want to convert it into elephant, first we need to delete the letter R, add a P right here, and replace the V with an H. And with this we have that the minimum edit distance is equal to 3. Now let's see how to calculate this. Let's talk about the Liebshtein algorithm. Alright, this is how the Liebshtein algorithm works. First, we need to create a matrix where the rows and columns correspond to the letters of our two words. In this case, face and fakes. It doesn't matter which we put as rows or columns, this algorithm calculates the same value in both directions. To start, we need to calculate the distance in this cell. First, we'll look at the value above and add 1. We place it right here. Then we add 1 to the value on the left and place it here. Now we look at the diagonal value. If the characters are different, we add 1. In this case, they are the same, so we pass the diagonal value without modifying it and place it here. Now we need to select the minimum value and place it at the result. This is the edit distance between this submatrix, which is 0 because both characters are the same. We continue now with the next cell, repeating the process. Again, we add 1 to the above value, add 1 to the left value, And in this case, the characters are different, so we add 1 to the diagonal. And again, we put the minimum value as the result. Now we add 1 to the above value, add 1 to the left value, and again the characters are different, so we add 1 to the diagonal value, this time is 3, and we take the minimum value and place it as the result. Now continue with the rest of cells. Alright, in the end we finish with this result, which means our minimum distance between our words is 2. This means that to convert the word face into fakes, we need to replace the C with a K and add the letter S, which is 2 operations in total. Now we have a way to calculate the minimum edit distance between any 2 words. Now we just need to use this algorithm to find words that are similar to the ones that the user typed. We just have to create a list containing our dictionary of words and iterate through the entire list, selecting these words that are similar to the target word. Or we can do something a little bit more efficient. Let's talk about BK trees. A BK tree is a data structure that fits perfectly with the Lichtenstein distance algorithm. To build this structure, first we add a word to the root. Then we add a second one and calculate the Lichtenstein distance between them. We create a new child with the distance value and keep doing the same for the other words. When we have 2 children whose distance from the parents is the same, what we will do is to select the child node that is already added and calculate the edit distance with the new node. Now the new node will be the child of the previous one and keep repeating this process. Alright, that's how easy it is to create a BK tree, but how can we perform a fuzzy search? First, we must define a threshold, which will be the maximum distance allowed to consider 2 words as similar. Let's say this threshold is 2. We allow up to 2 errors to select a word from the tree. We go to the root of the tree and calculate its edit distance to the target word. If the distance is less than the threshold, we add the word to the results. We can also add the obtained distance in order to be able to sort the list of results. Now we select all the children whose distance from the parent is less than the threshold and apply the search again recursively. In the end, we'll have a list of results that we can sort by similarity to the target word. This type of data structure doesn't only work with text, but also it is used for search images, audios, and even DNA sequences. If you can calculate the difference between 2 items, you can probably use some variation of this structure to perform a similarity search. Of course, for each particular case, they might be better tools, but it's a good starting point. Now we have a way to know which words are the most similar to the one entered by the user. So what we'll do is, if we don't get any matches from a certain term, we'll search into our dictionary for words that are similar below a certain tolerance threshold. We'll select the word with the minimum edit distance and that has more occurrences within the visited pages, which is the most likely to be the desired word by the user. This way, we can perform a search from that word again and add the pages containing it to our results. Now that we have these components, we are ready to define how the content in our database should look. The first and most important thing we need is the content of the page. We can create a list of pages that contain the set of words found on each page. This way, every time we need to search for a term, we'll search among all the pages that contain the given page. But this could bring us a big performance problem, because we will have to check page by page, word by word, those that match our search. This is incredibly inefficient, so let's turn the situation around, literally. Instead of pages containing words, we'll have words contained by pages. This is known as an inverted index, a data structure widely used in many types of search engines that allow us to obtain all the pages that contains a certain word immediately, or speaking more technically, in constant time. And this is the key of everything, the big secret. This is the part that will provide the performance to our search engine. Now, let's take advantage to talk about storage cost. This type of engines must store an enormous amount of information, so it is crucial to have tools that allow us to optimize space in disk as much as possible. The first thing we can notice is that in our index we have a lot of repeated information, which are the links of the pages that contains each term. We're wasting space by storing so much repeated information, so the first thing we'll do is to create a map that contains each of the pages we visit with an ID. This way we can replace the pages with this numerical value and save a lot of space. In the future, whenever we deal with pages, we'll use these IDs, and we'll only go back to the page link when we really need it. Another point where we can optimize space is with stop words. Stop words are basically common words that we can find everywhere, that are very repetitive and whose intrinsic value is little or even null. Some examples are of, very, the, in, and many others. A negative point about this word is that being so common, they are practically present in all web pages, so we'll have to deal with too much information. And on the top of this, they don't really add value to our search. If you think about it, when you search, who was the creator of the transistor, you can eliminate the words who, was, the, and of. Creator and transistor are enough for a search engine to understand what you need. This is an example of the space that we can reduce in a common text by removing stop words. Something important here is that each language has its own stop words, and probably we'll find stop words in one language that are very important words in another, so we can't remove them. To deal with this, we can first identify which language a certain phrase is, and then remove the stop words based on that language. Another thing we have to do with our words is to tokenize them so that we can get a more compact version of the same word, and also apply stemming. Stemming is a technique that simplifies words to their most basic part, so we can eliminate variation of the same word and focus on its meaning. For example, for the words play, playing, plays, we can convert them into just play, which is their basic meaning. This way we focus only on the essence of the word, not in specific variations. To achieve this, we'll use Snowball. Snowball is an algorithm by Martin Porter aimed to create the stems. An important thing is that we are talking about a family of algorithms. Each algorithm is different from each language, since each one has different rules. Here's an example of the Porter stemmer, which is a version for English. And again, to carry out this process, we need the language detector that we mentioned before. Alright, enough resource optimization. Let's move on the database structure. We already have our index and the word frequency map. Now let's talk about the links. As we mentioned before, we need to have the information about which pages point to each other. So another thing we have to do is to store this relationship. Basically, for each page ID, we'll save the IDs of the pages it points to. And this way, we'll be able to build the necessary graph to calculate the page rank of each page. Another thing we need is the list of words that we found on each page. This collection will be a map containing each word and the frequency with which it appears in our dataset. This will allow us to build our implementation of UC search. Now that we have the structure of our data, it's time to choose a database engine that suits our needs. My first consideration was to use a database optimized for working with graphs, like Neo4j or something similar, but the purpose of this experiment is really to learn how to do almost everything by hand. That's why the name of the channel. So I wanted to keep it as simple as possible, and the simplest is a key value store. An option that seems excellent for this is Redis. I once heard someone say that Redis is just a hash map as a service. I don't totally agree with that, but that's exactly what I need. And I know Redis has a lot of modules and interest functionalities that could save me days of work, but again, my purpose is to do it by hand. So I'll use Redis as a hash map. Now you're probably thinking there is a very obvious problem with this choice, and that is that Redis stores information in memory. I know I can use persistence in Redis, but that's not the problem. We are talking about saving the information of potentially millions or hundreds of millions of pages. I don't know about yours, but my computer doesn't have that much RAM. So, searching the web, I found SSDB, which is a database almost entirely compatible with the Redis API, but which stores all the information on disk instead of memory. And that's exactly what I need. So, I use Redis to develop the system, but SSDB for production. And as I said, the API is almost entirely compatible, so I don't have to change code between environments. Now that we have defined how our data will look and what database engine we will use, it's time to get all the information and store it. Alright, to get all the information we'll feed into our engine, we need to start browsing the entire web to find new pages to add. For each page we visit, we'll save its information in the database as seen before. We'll get all its words and save them into the inverted index. We'll also save the words into the frequency map and increase the counter for each appearance. Keep in mind that before saving these words, we need to filter out the step words and perform stemming. In addition to the words and their pages, we will need to extract the hyperlinks contained in the page and store them into the map that will contain the information about the relationship between the different pages. What we'll do is to create a queue in which we'll add some initial pages to visit. Pages that are important and serve as a starting point to find many other links to visit. We'll define the number of pages we want to download and iterate again and again until we have stored the determined number. For each iteration, we'll take out the first page in the queue, get its information, save it, and add the links we find in it to the queue to repeat the cycle again. Another detail to add is the importance of using concurrency in this part of the process, because each HTTP request takes time to complete. We can use this downtime to keep getting information from other pages, but it's very important that we limit the number of simultaneous calls that we can make at any given moment to avoid saturating the network and causing a performance drop. Something else we'll do is also to limit the timeout for the response from each page. If a page takes too long to respond, we can cancel the request and make room for other better optimized pages. Now that we've defined all the logic of our application, it is time to see how all of this has been implemented in code. By the way, all the code that you'll see now is available on GitHub. You can read it, clone it, fork it, sell it on the black market, I don't know, whatever you wanna do with it. The link is in the description below. Alright, first things first, let's define the environment variables we'll use. We set up the database connection, specify the initial web pages to crawl, limit the maximum number of web pages to download, just 3 million in this case, because my network capacity can handle much more than that, and determine the number of simultaneous calls that we can make. Now, in the main function of our crawler, by the way, I'm using Go, we load the environment variables, create our crawler with the database connection, and kick off the process. Here we add the initial pages to the queue and start downloading. At this point, we can see how we iterate until we reach the desired number of pages. In each iteration, we fetch the page information and save it to our database in order to build the index. And of course, all these calls are made concurrently, using the semaphore pattern to avoid overloading the network. Here is how we store everything in the database. Now let's move on to the ranker project. First, we define our ranker. To carry out the process, we'll be using this library from Daniel Cadenas, which is very efficient. This is how we calculate the page rank after building the graph. Finally, we save it to the database. Next, let's see the searching process as well. The first step is to build the dictionary for Fuzzy Search. To do this, we need to load all the previously saved words, and here's how we can perform the search. Lastly, let's see how we capture the user's request and do the search. First, we tokenize the search term, remove stop words, and apply the stemming. Then we search for the pages, merge them, get the page rank, sort them based on the previous defined parameters, and finally send the response to the client. The final part is the frontend. It's quite simple, so I don't want to use any framework, just pure HTML and JavaScript. Here's the home and result page, and here we can see the process of doing the search and rendering the results. And there you have it, that's all. Now the moment we've been waiting for. Let's see how it works. Okay, this is the result. We have this input here where we can type whatever we want. For example, I type Lady Gaga. And I got these pages. For example, here we can see information about the new movie of Joker. And some other things. And here we can load more results. And this is interesting, we have 3 million pages indexed and we are getting more than 3,000 results in just 9 milliseconds. It would be nice to test it out with more information, I don't know, about 100 million pages or something like that, but it is not possible for me right now. But I think it is enough for this test. Now let's try the Fuzzy search. If I type here Zuckerberg instead of Zuckerberg, we can find information about Mark Zuckerberg. So the Fuzzy search is working pretty fine. Now let's do some other searches. Now let's see what happens if I type Mona Lisa. I can find even the biography of Leonardo da Vinci. And that's it for this video. Let me know in the comments what you think. What will you do to make it work better? Remember to hit the like button and share this video. If you enjoy this type of content, do yourself a favor and subscribe to the channel. We will have many more videos like this. That's it from me and I'll see you on the next one. Bye!